Hi one and all, and welcome to today's mathematical methods video on inverses. Yes, part of the course over here in Australia. Now, if you are not Australian, don't worry about it. Inverses are universal across all maths courses throughout the world. So pitch in and watch, and hopefully you will learn something. Now, if you are new to my channel, my name is Darren, otherwise known as MaffsGuru, and it is always good to have new people along. If you can do me the greatest of honor, please. Over there in the corner is a little doohickey that asks you to subscribe to my channel. It makes me feel like I'm doing this for a reason and that people are actually watching. So your support and the support of a couple of your friends will be greatly appreciated. Now, inverses to me are freaking awesome, and they come up in exams all the time. There are two elements to drawing these things, or doing these. One will probably be drawing them, and one will be trying to find inverse functions or inverse relations and domains and ranges. And by the end of this, we will be looking at how to do all of that. This particular video actually has sort of a focus on exponentials and logarithms, which is very much the part of the course I am currently teaching to my students. So yes, I am a full-on qualified and currently teaching teacher, so all of this stuff is actually relevant. So by the top of what you're seeing now, by the end of this, we'll know how to find the inverse of exponentials, inverse of logs, know how to transpose, and being able to move these equations around using pencil and paper and your calculator, believe it or not, will be useful to you, and how to find the intercepts of inverse functions. Now, the intercept stuff is actually a little bit outside the scope. If you're following along with the Cambridge Essentials text, the Cambridge Math Methods textbook, then obviously this won't necessarily feature in it. It's come a bit earlier, but I like to recap because it's so important. Right, what is this finding the inverse? Well, basically, before you can find an inverse of something, you've got to actually know what it is. And generally speaking, when you're finding an inverse, you're doing nothing more than reflecting it in the line y equals x. You're taking a function or relation and you're reflecting it in the line y equals x. Now, I keep double erring there with regards to functions and relations because it's a bit of a trick. Now, bearing in mind, everyone by now should know what a function is. A function will pass a vertical line test. Yes, so you'll be able to draw a vertical line through a function or a graph or relation, and it will pass. It'll only cross once. It's important to know that for functions, it can only have an inverse if it's one-to-one. Now again, throwing out more language there. What on earth is a one-to-one function? Well, a one-to-one function is one where when you draw a horizontal line through it, you only cut through it once as well. So an example of a function would be y equals x squared, because it doesn't matter where I go there and draw a vertical line, it'll only ever cross through that once. However, if I draw a horizontal line through there, well, that now isn't one-to-one. How do we make a one-to-one function? Well, actually, we fudge it a little bit. What we do is we say, well, okay, I know that if I cut this thing in half and actually just limit my domain and pretend that half of it doesn't exist, then it becomes a one-to-one function. Now, with that one-to-one function, I can go on and find its inverse function. Don't be tricked in exams. Sometimes they can say find an inverse relation, and people get very confused and make silly mistakes, but don't. So it's so important to notice that for any maths that you do, if you're asked to find a one-to-one function, make sure that that function is one-to-one first. See if they try and trick you. So let's look at what an inverse of a function is using a graph as an example. So I've drawn one here, and what you'll notice is there's lots of graphs on here. So I've started off with the idea of y is equal to 2x squared. That's my original function. But as I've just said a moment ago, if I was to draw that, it would be that. That is not one-to-one. So what you'll notice is here, using desmos.com, I've actually limited my domain. And I've said, well, I'm only interested in part of that function. I'm only interested in the values between 0 and 6, hence making it one-to-one. And that is this red line here. Awesome. Then what I've done is I've drawn on my line y equals x, which is the dotted blue line. And then I've gone away and I've gone, well, okay, for me to then draw my inverse function, I've got to actually do some algebra. And we'll do a little bit more of that in a moment. But what we know is that when we're finding the inverse, because we're reflecting it in the line y equals x, it means my x and my y values are swapping. And obviously when we do this algebraically, that's why we swap the x and y values. When you're reflecting in the line y equals x, you're actually just making your x values your y values, and your y values, your x values. And so in the formula, we swap it over. So I would say now x is equal to 2y squared. So I would have x on 2 is equal to y squared, and then square root both sides, I get the square root of x on 2. Now, if you've just written that and you're happy with that, I'm really, really sorry, but there's a classic mistake here, because when you square root something, you have to do plus or minus. Now, that's an issue, because what that now is giving us is actually two graphs. Because when I draw the positive of the square root of x on 2, I get this green thing here. I get that green function there, but there's also a negative. Remember, when I square root, I have to have the negative, and that's what that blue line is. So this blue line here is the negative of the square root of x divided by 2. So, in an exam, which one do we want? Well, we obviously want the green one, because that's the one that's going to be the inverse. That's the one that's so obviously visually reflected. And in a methods exam, you would be expected to discount one of those functions and write a statement that says, because I'm looking for the inverse, I would be choosing the positive of the square root of x on 2. Yeah, so I did this just to show you how methods can trick. But there you go, there they are. Now, knowing the function is inverse is really, really important. We've done all of that, but drawing the original function actually helps us shortcut some really difficult maths later on. And the reason being is the domain and range of our original function can help us find the domain and range of my new function. Because if you think about the idea of the fact we're swapping x's and y values, if I'm literally doing that, if I go back to, or this is a more sort of expanded, and I've just taken the part. If you look at this, what was it? Our red was the first one. Our domain there was given by 0 to infinity. Yes, and it is including 0 because we've got that coloured in dot. My range is also given by 0 to infinity. Now, this isn't possibly the best example. If I could have chosen something else, I would have done. But if I am swapping my x and my y values to get an inverse, then hopefully it makes sense that my domain and range are swapping as well. It must be, because my x values become my y values and my y values become my x values. So my domain and range swaps. And in which case it makes so much more sense when they give you an original equation, find the domain and range of it, and then you've automatically got the domain and range of your inverse function, because you can just swap them over. I'll talk a little bit more about that in just a moment. So let me think. Last thing you need to know, and again, points of intersection is this point here. Now, what you notice is when we try and find points of intersection, generally speaking, we will teach you to put the two equations equal to each other. Yes? But I can promise you the maths behind that will get gross, particularly in a methods exam where they will undoubtedly choose something that's not particularly nice for an inverse function. So as I say here, yes, you can put f of x equals f to the minus 1 of x, and job done. You would grossly end up with your point of intersection. But the interesting thing to note is this line y equals x, which also goes through any points of intersection. You'll notice there are in fact 2 points of intersection there. 0, 0, and 0.5, 0.5. So using the fact that we have y equals x there, and we know that this here is y equals f of x, and at that one point where they cross, this y value and this y value are the same. Well, if they're the same, then it must mean that f of x and x are also the same. And there we go. To find the points of intersection, you can actually put your original function just equal to x. It's mind-blowingly awesome. Theoretically, you could do the same with the inverse. It works in both cases. But generally speaking, your inverse function is going to be gross. Now, that's a little bit beyond the scope of what this particular lesson is about, but I think it's important to recap. So, finding inverses using exponentials and logs. I rave all the time when I'm teaching this to make sure you draw a sketch of any graph that you are trying to find the inverse and the domain and the range. As I said just a moment ago, by finding the domain and range of the original function, we've got the domain and range of the inverse like that. So here are some examples, again, extracted from the Cambridge Mathematical Methods Unit 3 and 4 textbook. Thank you, Cambridge, for allowing me to use them. And what have we got here? So find the inverse of that function. So hopefully everyone out there in internet land who's watching this understands what f colon r mapped onto r comma, f of x equals e to the x plus 2 mean. So what it's saying is, there is my domain, if you remember. So my domain here is all real values. Thank you very much. I'm going to write that down because I'm telling you now that's going to be important. And it says my function is e to the x plus 2. Now, boys, I'm so sorry, but stereotypically you'll be like, yeah, it's all right, don't need to draw this. I guarantee, please draw this thing. So I've done a quick sketch on Desmos. The reason being is it now tells me quite wonderfully what my range is. So there is my range, and that's going to give me from 2 to infinity. Yes, remember my asymptote there, it has an asymptote, so it won't ever touch 2, so it can't include the value of 2. Now, why have I done this? Well, because I've now automatically found my domain and range of my inverse, which I'll come back to in just a moment. All I need to do now is find my equation of my inverse, and that is going to be beautifully done. Let's zoom in a little bit to give myself some space. So we now know that y is equal e to the power of x plus 2. I'm going to find the inverse. Let's flip them over. So x becomes e to the y plus 2, and I now want y on its own. How do I know I'm going to use logs for this question? Because I've got a floaty y. I've got that floaty y, and I know that I can use logs to bring the y down. First thing I'm going to do, though, is get rid of that 2. So x minus 2 is e to the power of y. And now I'm going to take logs of both sides. What log base am I going to take? Well, e, because I've got e to the power of y, that's what I'm trying to get rid of. So I get the log base e of x minus 2 is equal to y, and whoop whoop, thank you very much, I am done. Well, no, not quite, because I'm going to actually, they've given my equation in function notation. I'm going to give them the inverse back in function notation, and I'm going to do my domain and range. So therefore I know that f to the minus 1 colon, what is my domain? Well, remember, my domain of my inverse is the range of my original, so I'm going to write 2 comma infinity mapped onto real, because that's the codomain, and until university that's exactly what it's going to stay. And then I get f to the minus 1 of x is equal to log e of x minus 2. Now, because the question says state the domain and range, I'm going to say my domain therefore is equal to 2 comma infinity, and my range is equal to real. Now, if you don't believe me, bang that particular function into your Desmos calculator, and I promise you that will be true. Now, I think this is fairly trivial. These questions are awesome. They are formulaic, so long as you draw that sketch. Example 2 from the textbook, interestingly, sort of changed tack a little bit and says, right, rewrite that equation with x as the subject. It just wants me to transpose it. So rewrite the equation with x as the subject. Right, so we have y is equal to 2 log e x plus 3. It's not asking me to do the inverse. I don't swap the x's and y's. I'm going to do y minus 3 is equal to 2 log e to the x. Now, interestingly, one of my students then said, well, what's the best thing to do with the 2? And I was like, what do you mean, what's the best thing to do with the 2? And she said, well, I could write that 2 and put it up here and then square root. And I was like, oh, interesting. You could, but in my view, that would make things a little bit more complicated. I'm just going to divide both sides by 2 to give me y minus 3 divided by 2 is log e to the x. And how am I going to get rid of that log base e? Well, because logs deal with powers, I'm going to raise everything to the power of e. That's the way I'm going to get rid of that log e. So here is e to the power of y minus 3 on 2. Notice the use of brackets so that the examiner knows that you're keeping that all together and it's an exponent, is equal to the value of x. Wow. Love this stuff. Example 3, we go back again, Cambridge. But okay, we'll deal with it. Find the inverse of that function. Once again, do we understand what this means? Right, yes we do. We have some sort of a function that is limited between 1 and infinity and beyond. And this is my function here, and once again state the domain and range of the inverse. To find that domain and range of my inverse, what do I need to do? Yay, I'm going to find the domain and range of my original function. And to do that, I have once again fired up my trusty Desmos. You'd probably use your CAS calculator or just sketch it. And lo and behold, there is what my function looks like. Now, we could have probably guessed a lot of this. Remember, we've got to try and think of all times of transformations. So that 2 there is a dilation of factor 2 away from the x-axis. This is a translation 1 unit to the right, and then this here would be 3 unit translation up. But drawing a quick sketch on my calculator has done all the hard work for me. So what I'm going to do now is over here I'm going to write, well, I know the domain of that function is actually 1, infinity, which they already gave me in my function notation. And my range is equal to, or my rage is equal to, what is my range? Well, in fact, in this situation, all real values. Right, so that's going to help me a little bit later on. Let's do some algebra to find the inverse of that function. So we've got my original function as y equals 2 log e of x minus 1 plus 3. So I'm going to swap my x and my y value to log e of y minus 1 plus 3. Okie dokie. So let's do it again. So we're going to get x minus 3 is 2 log e of y minus 1. And divide both sides by 2 gives me x minus 3 on 2 is equal to the log e of y minus 1. We can do this now because I've got a log on one side and I've got something else on the other side, and so I'm going to raise it all to the power of e to get rid of that log e. So, ladies and gentlemen, we get e to the power of x minus 3 on 2. Again, remember those brackets, is equal to y minus 1. And so y, my new inverse function, is e to the x minus 3 on 2 plus 1. There we go. What is my domain range? I'm just going to move it up a little bit, bringing that back in so it's useful. So my domain, let's write it now as x is in all real values and y is in 1 to infinity, not including either of them. And we're going to finish this off with function notation just so that we don't lose any marks. So my domain is real, mapped onto real, of f to the minus 1 of x is equal to e to the x minus 3 on 2 plus 1. Ladies and gentlemen, see, this is so formulaic, it is so repetitive. And last part, rewrite the equation. P equals ae to the kt with t as the subject. So it's just saying, let's get t down. I don't want it to float anymore, let's get it down. Let's do that then. So p is equal to a e to the kt. First thing I'm going to do is divide both sides by a. So p on a is equal to e to the kt. Right, I've got e to the power of something. What am I going to do to get rid of that? I'm going to log both sides, absolutely, base e. So I get log base e of p on a is equal to kt. And divide both sides by k. Yes, now there's lots of ways of doing this. Lots of my students went log of e of p of a divided by k is equal to t, and unfortunately that just looks gross. You've effectively got a fraction on a fraction, which mathematically isn't particularly nice. But what you can also do is realize that divide by k is the same as 1 on k times log e of p on a equals t. And there we go. That is the answer I would be very happy to see in an exam. Log base e of p on a. There we go, ladies and gentlemen. I have rearranged with t as the subject. Now, the great thing is, as I say here, we can use your CAS to help you do this. How? Well, let's fire up the CAS and have a look. Now, knowing when to use your CAS obviously is the most important thing here. In methods, you are allowed to use it for multiple choice and extended response, and they are all in one paper. The other paper you won't be able to do. So you have to be able to do this, both pencil and paper, and using your CAS calculator. So what I'm going to do is I'm going to hit my main function here, he says, and his calculator. And what I'm going to do is I'm actually going to put in the equation they've given me. Now, they've got 2 log e x minus 1. Your calculator is clever, but it's not that clever. So the first thing you need to do is you actually have got to put in the equation with you already having swapped the x and the y value. So I'm going to write, let's write x is equal to 2 times, we want log base e. Where is my e? It's a very good question, actually. Where is my e? Let's put e there. Log base e of x minus 1, no, y minus 1. And what else are we doing? Plus 3. Okay, so having put my equation in, highlight it, and then hit interactive, equation inequality, and solve. And it will say, well, what do you want me to solve for? We don't want to solve for variable x, we actually want to solve it for variable y. And when I press equals, and out comes y equals e to the minus 0.5x minus 1.5 plus 1. Now, it's not particularly nice because remember when we had it, we had x minus 2 all on 2, x minus 3 all on 2 plus 1. Using a calculator is great. It can certainly give you an indication, but I'd be careful in terms of how you write the answers. In methods, you have to always write it as exact form, and so 1.5 and 0.5 wouldn't be accepted as an answer. But there we go, it's just a way of using your CAS. The good news is, if you are watching and still watching, that is the end of Inverses. Thank you so much for taking the time in watching. If you haven't already done so, can you do me a favor and give me a shout out to a few of your friends and get them to subscribe if you find the videos useful. And if you haven't already done so, over there is a little doohickey for you to click and subscribe. Otherwise, the video is loading below it for methods 3 and 4 as well. It's really good to see you. Thank you so much for taking the time in getting this far. Let me know what you think by leaving a comment below. Otherwise, I look forward to seeing you in another video. All right, take care. MaffsGuru, signing off.